will be completed by the next class. Okay, by tomorrow. I'll try to complete it by tomorrow. I will give you the material for the 50 unit as early as possible. Okay, you go through the materials, online materials that I have sent to you on or before next week Tuesday. Okay, I'm giving you 1 week time. You go through those materials. I will come for 1 hour for the next week, 1 hour or more as per your requirement. Okay, and I will be waiting for you to ask your doubts. You have to ask your doubts there. Okay, if you have any doubts, okay, first you want to go through the material, then only you can ask your doubts. Okay, go through the material, try to understand it, because this 3 units, this last 3 units are the one which is going to get you more marks. Okay, and it's also very easy to. Okay, if it is there, I would have explained how far it is easy. Okay, fine. Even now it's not a bad time to say it. Okay, we'll go through the subject. Okay, oscillators. Fine. Okay, so oscillators, as you know, what is an oscillation? So you want to generate some frequency. You want to generate some signal with some frequency, with some particular frequency. That is the oscillator, right? Okay. So this oscillations can be of any form. Either it can be sinusoidal or triangular. Wave. Okay, whatever the oscillations, what is those different? You are frequency. Have gone away in the frequency. You must have tuned that frequency in your oscillator. You put some AC and AC signal. So that is clear. So I'm having some formal definition here. From this oscillator is an electron frequency. So that is the point to notice. Okay, if you see here, okay, this is oscillator, and I'm underlining this is because yes. My voice is not clear. Okay. Is it clear now? Still not? Okay. Yeah, is it clear now? Hello? Guys, can someone unmute and let me know whether the voice is clear or not? Now it's clear. Okay, fine. Okay, I think it's good to go now. Okay, fine. Fine. Okay, so here there is a word that is called without an external signal source. Okay, so in why this term is there is, see, if you have any doubt, any problem with the audio, or if you have any doubts, unmute yourself and let me know, because I am in the window of this PPT. Okay, I can't see what you are typing now. Fine. Okay, guys, I'll go ahead with the presentation. Okay, now here there is a line called without an external signal source. That is the main point to be noticed, because in your RC coupled amplifier you will be giving some input, you will be giving some AC input, so that it will give the amplified version of that input signal, because you will be giving some 50 millivolt or something, and you will be getting an output as a 2 volt or something, because it is based on the gain that is provided by the amplifier you have just designed. Okay, here in the case of oscillator, it wants to generate that oscillation. Okay, it wants to generate, you are giving some input, right? It wants to generate that input. So you can't have an input there. Your circuit itself has to generate this oscillations. Okay, so that is the purpose of the oscillator. So oscillator is an electronic circuit that generates a periodic waveform. Periodic waveform means it should not have any shift in the phase or amplitude. Okay, the phase and amplitude, everything should be same. Okay, if there is a sine wave, then it has to be a perfect sine wave. The zero crossing should be proper everywhere. Okay, that's why it is a periodic waveform. Fine. Then moving on. Okay, so as I said, there is no input is required, and applications are, see, the main application of the oscillator is in your communication side. Okay, and in the communication side, you need you are say we are having a radio. You hope you know about the radio. You must have at least seen a radio that is being operated by tuning the frequency. So how you are tuning the frequency is, you will be tuning the oscillator frequency. Okay, you will be tuning the oscillator frequency. So how to tune that oscillator frequency is, you will be changing the value of the capacitor. It will be a variable capacitor. If you see, if you are keep on adjusting that knob, the value of the capacitor will change, capacitor or resistor will change, and accordingly the frequency will change. The frequency of the oscillations will be changing. So accordingly your signal is received. That's how you achieve a FM communication, frequency modulated communication, or amplitude modulation there in your basic radio. I am talking about a basic radio, AM FM radio. Okay, so that is the first point. And the second one is it is used in digital systems as well, because when you open a system, when you see your motherboard, when you open your desktop system, or your particularly your laptop, you can see there is a oscillator will be there. There is a crystal oscillator will be there. Okay, that crystal oscillator is required to generate some clock frequency. Okay, it has to keep on generating that clock frequency. Fine. Okay, so that there also the oscillator is a very crucial part. That plays a very crucial role there. And finally, you can see that in a CRO or DSO recently, there is an oscillator. Okay, oscillators are there everywhere. Digital, when digital is involved, digital or analog, whatever the system is, particularly when digital is involved, a square wave oscillator is completely required. And in the case of your communication system, there is a sine wave oscillator will be there. Okay, fine. Now we are going to explain how this oscillator is operating without an input. Because without an input, how can an oscillator, how can a circuit can give output? I am not giving any input. How can a system can give output? That's a natural question arises whenever we discuss about an oscillator. Okay, for that we consider this circuit. Whatever I'm discussing, most of them are taken from your Robert Boylston book. This diagram is available in the Robert Boylston book. Either you refer the Boylston book or just refer my slides. Okay, okay. Now here you can see this A is a normal amplifier we have designed. Consider that is an RC coupled amplifier, and beta is a feedback network. Beta is the feedback network. Basically, you see beta in this place. Okay, for a change, for explaining the oscillator operation, I placed this beta here. There is no other difference with this circuit. This circuit is no different from what you have seen from the amplifier. You must notice that amplifier is a negative feedback circuit. Feedback amplifier is a negative feedback circuit, and the oscillator is a positive feedback circuit. Okay, these two are the key points that you have to have in mind. Because in the input voltage, if you apply whatever that is going to input, that will be in phase. That voltage, feedback voltage, will be in phase with the source voltage in case of oscillator operation. That means P is equal to V, source input, plus yes, yes, yes. What is breaking? Okay. I will disconnect and we will connect it again. Okay. Feedback amplifiers, your input and your part of the feedback network output, if they are in out of phase, then your input will be VA is equal to VS minus VF. Okay, here VA is equal to VS plus VF. Okay, that is the only main difference between the oscillator and an amplifier. Okay, so it has many reasons for doing that. Okay, firstly, we consider a circuit like this, and there we can see that this this beta network is generally, it is given here, it is given here in your feedback amplifier. Here also the same setup, only thing is the beta is connected here. There is no other difference between them. When the switch is not connected, when I am giving the input to VA, yes. Now is it visible? Yes. Okay. Ah, okay, fine. Okay, so this feedback network is generally connected here. Okay, for your feedback amplifier, and your oscillator is also no different. The only thing is the VF here is actually minus plus for feedback amplifier, whereas here it is plus minus. This has to be noticed. Okay, this is because your part of the output is made in phase with the input signal that we are giving. Okay, that is the means of the positive feedback. Okay, and I'm erasing all the inks right now. Okay, now the switch is, consider the switch is open. Okay, and we are giving an input VA. So after entering into the amplifier of gain A, okay, we will be getting output of A into VA, and when this output is entering into the feedback network beta, beta is the gain of the feedback network. Consider beta is the gain of the feedback network. Then we will be having the output as, that means output is represented as VF because it is going into the feedback network. That's why the output of the feedback network is VF. So we have beta into AVI because AVI is the input here and beta is the gain here. The corresponding gain is multiplied with the input, and we get the output as beta into A. That means A beta into VA. Okay, this is when the oscillator, this is when the switch is open. Okay, so when the switch is open, no oscillations occur. And that means when you are giving input, you are just, I mean that you are giving some input and you are getting some output at the amplifier. That amplifier is with the gain A, and you have the feedback network. This feedback network will also have some gain, or we call that as an attenuation for some purpose. Okay, and your input is AVI now, and when it is entering into the beta, the feedback network, your output will be beta into AVA. Beta is the gain of the feedback network, and AVA is the input to the feedback network. Okay, fine. Now consider a fixed CS voltage is given. That's what I have said so far. Fixed CS voltage means actually it is an imaginary voltage. Okay, fixed CS means, what you mean by fixed CS? Real story and fiction. Fiction means something that is not actually happened, but you will assume that it has happened. Okay, uh, you must have known about what is the difference between a fiction and a real story. Okay, so consider fixed CS voltage. This VA is a fixed CS voltage right now. VA is not actually given physically, but you assume that VA is given right now. Okay, that's why we have this input and the output. Here beta A is known as the loop gain. Okay, and you can clearly see that VA, VA and VF, VA and VF should have equal phase and proper magnitude. Okay, equal phase. They must be of equal phase, and the loop gain must be maintained at 1. Okay, this is the requirement of a, this is the basic requirement of an oscillator to operate. Okay, for oscillator operation. Okay, we will see this in detail. Okay, and when I move to the next slide, the same circuit. What happens when the switch is closed? Okay, that's what we are going to see here. When the switch is closed, okay, when the switch is closed down, okay, and this fixed voltage VA is removed. That means you have given a fixed voltage and you have taken that away. Okay, the fixed voltage VA is removed. What happens is you must have a sufficient feedback voltage. That means VF should be sufficient enough to drive your amplifier. Okay, you have to make sure of that so that you have oscillations there. Okay, so this is the main requirement of an oscillator. Okay, your feedback voltage is sufficient every time. It should be sufficient enough to drive your amplifier A. Okay, that is, amplifier A is the main amplifier and beta is the feedback amplifier. Okay, so to maintain the sustained oscillations, the loop gain beta A should be equal to 1. Beta A is equal to 1 means there are two conditions. One is amplitude of A beta should be equal to 1. Okay, amplitude means magnitude of A beta should be equal to 1. And the phase of the, I couldn't write it properly, and the phase of the beta A should be equal to 180 degree for and the phase of it should be equal to 0 degree or multiples of 360 degree. Okay, then only we will have a beta A is equal to +1. We have a +1 here, so the angle should be 0 degree or multiples of 360 degree. Okay, this is the loop gain angle to have a sustained oscillations. Okay, this criterion is known as the Barkhausen criterion. Okay, this Barkhausen, because of this Barkhausen criterion only, oscillations will occur only if the circuit satisfies, if the oscillator circuit, if we are considering the circuit, if the circuit satisfies this Barkhausen criterion, that is A beta is equal to 1 or it is greater than 1. Okay, at times it will be greater than 1, then only there will be an oscillation. Okay, fine. So we will see a little detail about Barkhausen criterion because this is very, very important. Barkhausen criterion is very important. Okay, now Barkhausen criterion will give the set of conditions that are required to make a circuit oscillate. Okay, fine. Okay, now as I said already, oscillators work on the principle of positive feedback. Positive feedback is also known as the regenerative feedback. Okay, and for that we will be taking a fraction of an output to the input, and we will be maintaining at a proper phase. We will be maintaining that feedback output as a proper phase, so that the condition A beta should be equal to 1, the magnitude of A beta should be equal to 1, and beta should be equal to 0 degree on the multiples of 360 degree. Okay, this is the basic criterion or way of Barkhausen. Okay, Barkhausen is a scientist. He has devised this criterion. Okay, for oscillation. Fine. Okay, now we are talking about some fixed voltage and all those things. Now, how a practical oscillator works? That's what we have to question here. Okay, so when we are considering a practical oscillator, see, remember your whatever circuit you are designing, there involves some thermal noise. Okay, there is some noise due to that due to the thermal power. That means thermal runaway or your current IC, there is some heat is producing. Because of that, some noise voltage will be there. That noise voltage is very, very small initially. Okay, and that noise voltage is being automatically be an input to your oscillator. Okay, and that noise voltage is very small initially, and it will be keep on growing as the feedback operation continues, and after a particular point, that particular sine wave will be automatically generated. Okay, so from where it is getting generated is, it is from the thermal noise. Thermal noise, your sine wave is actually getting generated, sine wave or whatever wave we're considering, because thermal noise can be of any frequency or any voltage. Okay, particularly the magnitude of the thermal noise is very, very small. Okay, we want to amplify that thermal noise and amplify only one frequency of that thermal noise. Okay, so that is our aim. In as I said, those are all the points that is being listed here. no input signal will be given. We have talked about a fixed voltage in the while discussing about the Part-1 criterion or the oscillator operation, but practically we can't give that fixed voltage because that is a real story. Okay, and noise voltage will be there. Initially, beta A is set to be greater than 1. Why it is set to be greater than 1 is because your noise voltage is very small, so that you can't have an oscillations of in the range of just a microvolt or nanovolt. You need to have your amplification. You need to have some amplification, and you want to amplify at least till 1 volt. Okay, so what we are doing is initially we said beta A should be greater than or equal to 0, greater than 1. Okay, and we will amplify the noise voltage. Okay, in the noise voltage, it is not necessary that it has to be in only one frequency. It will be the collection of frequency. What this feedback network will do is it will select only one frequency, and it will start oscillating at that frequency. It will start amplifying that frequency. Okay, so that is the beauty of this practical oscillator. Okay, we will be designing some oscillators for that for your lab as well. Okay, fine. Okay, once as I said, once you are amplified, once your noise voltage is getting amplified and it reaches a particular level, this beta A condition will be automatically equal to 1, because your oscillator is designed in such a way that it should not go beyond that. Sine wave should not go beyond such certain value. Okay, so in that way your oscillator has been designed. So after a particular in the signal when a particular value is reached, then this beta A will be equal to 1, and automatically we have a signal like this. See, whatever I said right now, here you can see initially there is a noise voltage, that is very small voltage, but this small voltage is will be useless. Okay, so we want to develop this noise voltage. We want to amplify this noise voltage. When beta is set to be greater than 1, this will be slowly growing. This small noise voltage will be slowly growing, and at a particular point we will make this beta A should be equal to 1, so that this when I consider that this size of sine wave is enough. If you check the output of the oscillator, you will be having some oscillations there. Either it will be a sine wave or a triangular wave, whatever it is. Okay, so this oscillator generally oscillates at only one frequency. Remember, okay, and this one frequency is being selected by your feedback network. Okay, so your feedback network, whatever the feedback. And that is added with the source signal. This is the source signal, and that goes as an input to the feedback, the input to the actual amplifier without feedback. Okay, so then what happens to the gain of the amplifier with the feedback? So we have included the feedback now in this equation. We have included the feedback voltage now. Now we have VA is equal to V output divided by VS plus VF. This VA, instead of this, the place of this VA is substituted in this equation, so that we have V output divided by VS plus VF. Okay, in the place of VF we will be substituting beta into V naught. As we know, these things are all repeating only. All I have done is changed this. Previously it was minus here. Okay, now I have changed this to plus. Okay, now the feedback voltage is nothing but a fraction of means a part of your output. Okay, that part is decided by beta, a part of your output, beta into V naught. If you see that diagram, it will be very clear. Okay, on rearranging those equations, take beta V naught to one side and Vs to another side, and we have gain with feedback as AF is equal to A by 1 minus A beta. Okay, remember, this is the final equation of your positive feedback. In your negative feedback, you have AF is equal to A divided by 1 plus A beta. Okay, that is the only difference between the positive and the negative feedback. If there is a negative feedback, then you will have A by 1 plus A beta. If you have a positive feedback, you have A by 1 minus A beta. Okay, fine. Okay, now we will discuss about the types of oscillators. Basically, your feedback circuit, how it is constructed, feedback circuit, how it is constructed. Based on that, your oscillator types are classified. Either you can design your oscillator with RL, RC, or RLC components, combining all the three components, or L and C components. Okay, and the oscillators can be classified as RC oscillator, LC oscillator, crystal oscillator. Crystal oscillator, we will discuss that later, and the relaxation oscillator. Okay, relaxation oscillator, we have. I was about to discuss about the UJT oscillator at that time. That is actually the relaxation oscillator. We will discuss that later. Okay. Right now we will be discussing only the RC oscillator. RC means resistor capacitor oscillator. The feedback network will be consisting of only the resistor and the capacitor elements. Okay, this RC oscillator is classified into two types: RC phase shift oscillator and Wien bridge oscillator. Okay. Okay. First, we will see what is the Wien bridge oscillator is. Okay. The RC phase shift oscillator we will see for the next class, or I will give. I will start on RC phase shift oscillator. Okay. Fine. Okay. This is your Wien bridge oscillator. Hope in your 12th standard you must have heard this word Wien bridge. Okay. Here, this particular part is actually your feedback network. Okay. Now, you must be wondering who this guy is. We haven't seen this guy before. This guy is op-amp. With the op-amp you will be studying in the next semester very deeply. You will be studying in the next semester, that is IC741. Okay, it has the inverting terminal and the non-inverting terminal. So whatever input you give it inside the op-amp, consider this is an op-amp is nothing but an amplifier. Okay, it will have two inputs. If you have a negative, if you give the input in the negative side, negative terminal, here you have the negative terminal. If you give the input to the negative terminal, then your output will be inverted. If I am giving a sine wave, that means from 0 it will be going up and then coming down. If I am giving that in the negative terminal, then you will be getting the exact inverse of that. That means from 0 it will be going down and coming up. Okay, so that is about the inverting terminal. And the non-inverting terminal is generally a normal amplifier. If you give the sine wave, the same sine wave will be appearing at the output with the increased gain or amplitude. We can say with the increased amplitude. Okay, so this is about the op-amp. Don't get too fussed out by this word op-amp. Op-amp means operational amplifier. Consider that it is an amplifier. We are not going to discuss more detail about that amplifier. Right now we are having an amplifier, and this is an amplifier A, amplifier with gain A. Okay, and this is a feedback network beta. Okay, just have this in mind. Okay, we will go to the Wien bridge oscillator operation. Okay, see, and the frequency can be adjusted by varying the values of R1, R2. As I said earlier, the frequency of your oscillation is based on the design of your feedback circuit. Okay, design means values of your RNC. Okay, how your RNC values are decided. This RNC value actually decides the frequency of the oscillations of your oscillator circuit. Okay, now this R3 and R4 forms the feedback path. This is another feedback path. Okay, right now we are not worrying about this R3 and R4. We are not worrying about this. Okay, we are worried about only R1, R2, C1 and C2. Okay, we are redrawing this. Take this. We will redraw this Wien bridge oscillator so that we will be having a circuit like this. Here you can see that. See, I have values substituted, some values. This is an example problem. You can go and solve it there. Okay. If I am redrawing, you can see the input is given to the positive terminal. I mean the non-inverting terminal of your op-amp, so that your input, if your input is having a phase shift of 0 degree, then your output will also have a phase shift of 0 degree, because there is no phase shift has been introduced there. Okay, so we have to make sure that this Wien bridge feedback guy, right? This guy should not be introducing any phase shift to your signal. Okay, so we want to verify, we make sure that this guy should introduce only 0 degree of phase shift, and it should have anyway it will be having some gain beta. Anyway, it will be having some value beta will be there, and based on this value of beta, we will be setting the gain of this op-amp. Okay, now we will derive what is the value of beta for this particular Wien bridge oscillator feedback circuit. Okay, so now if you take this circuit particularly, this will be having a resistor, a capacitor, and a resistor and a capacitor in series. You can see that a resistor and a capacitor in series, and a resistor and a capacitor in parallel. Okay, this is the circuit we are having. So I am redrawing this. I am taking this part alone, this particular part alone. We are going to analyze this particular part alone. Okay, in this Wien bridge oscillator to understand the feedback network of your Wien bridge oscillator. Okay, now this has been redrawn here. You can clearly see that the resistor R1 and C1 on here. See, either you can have C1 here or R1 here, not a problem. This can be interchanged, not a problem. Okay, anyway, they are in series only, so it won't create that big problem. Okay, here you have another parallel combination of R and C. Okay, this is the same feedback network that we have seen before. Okay, I'm just taking that particular circuit alone. So we are giving an input V in dash, and we are getting an output V output dash. This is an intermediate input and output of your. This is just the input and output of your particular RC network, RC feedback network. Okay, whoever mic is on, please mute yourself. Yes, whose mic is on, please mute yourself. Thank you. Okay, now we will discuss about the circuit. Okay, here if you see this particular circuit, this is nothing but a high pass filter. Why it is a high pass filter is, see, if you are transmitting some signal of higher frequency, of lower frequency, then this capacitor will be a open circuit, correct? This capacitor will be open circuit, and it will not, and your signal will not pass this line, this particular line. Your signal will not pass this particular line. Okay, whereas if I am passing some high frequency signal, then your capacitor C1 will be short circuited there, then it will be passed. That's why it is known as a high pass filter. Okay, whereas what we have here is a low pass filter. Okay, so when I am having a low frequency signal, then your capacitor will be open circuited. Then whatever voltage that is appearing across your resistor R2 will be appearing in the output. Okay, what happens when a high frequency signal is entering here? When a high frequency signal is entering here, then your capacitor will be short circuited. Then your output voltage will be obviously equal to 0. Okay, that's why this circuit is having a low pass filter and a low pass filter here and a high pass filter here. Okay, yeah, please mute yourself. We are facing a problem. Yeah, thank you. Okay, so this is about your low pass. This is about your Wien bridge oscillator and its feedback network. You have a low pass filter and a high pass filter. Okay, then which frequency will pass? That's a biggest question, because your low pass filter will stop the high frequency components. Your high pass filter will stop the low frequency components. Then it will allow only very few frequency. Okay, that frequency, that very few frequency, consider only it passes only one frequency. That frequency is known as the resonant frequency. Okay, high pass filter will allow the low frequency. It will not allow the low frequency component. Low pass filter will not allow the high frequency components. But at least it will pass only one frequency component, that is known as the resonant frequency. That means at only one particular frequency, my output will be maximum. Okay, so that frequency is known as resonant frequency, and your feedback network is now acting like a notch filter. If you see the frequency response of the notch filter, it will be like this. Okay, so here it will be some a frequency, resonant frequency FR will be there. Okay, the peak frequency is at a particular frequency your output is very high. That frequency is known as the resonant frequency. Okay, fine. Okay, so what happens at the resonant frequency? That is a big question here. Okay, your see your phase shift of the circuit should be equal to 0. The phase shift that is introduced by this circuit is equal to 0. That means if I am giving a normal sine wave as like I have given here, then my output should be the same. It should be like this only. Okay, it shouldn't be like whatever I am drawing now. Okay, it shouldn't be like this. Okay, this is wrong. Okay, this is 180-degree phase shift actually. This shouldn't be happening. Your phase shift that is introduced by this circuit should be 0 degree at the resonant frequency, and the gain we have is we have for this feedback circuit is 1/3. This 1/3 value will be derived now. If I am taking this beta value for this, that means beta means the gain. Okay, in case of feedback network, it is the gain, or we can call that as an attenuation as well. Okay, fine. Okay, now at the resonant frequency, if we have that, yes, any problem with the audio, guys? Any problem with the audio? Can someone unmute and please respond? Yeah, okay. Thank you. Okay, mute yourself, please. Okay, so at the resonant frequency, if you see, if my values of the capacitor and the resistor R1, this R1 is equal to this R2, and the C1 here is equal to C2, then we have the resonant frequency formula as FR is equal to 1/2 pi RC. Okay, in case if R1 is not equal to R2 and C1 is not equal to C2, that capacitance and the resistance are not equal, then my resonance frequency is given by square root of R1 R2 C1 C2. If I put R1 is equal to R2 in this equation, you can see you will be directly getting the resonant frequency equation here, resonant frequency expression here. Okay, so this is about your Wien bridge oscillator. We will now know how we get the beta is equal to 1/3 value here, and how this resonant frequency is getting the expression of 1/2 pi RC. Okay, so that will be discussed now. Okay, I'm moving on to the next slide. So I am taking the same network. We are considering here this particular high pass filter network as the impedance of this particular high pass filter network as Z1, that is the effective impedance as Z1. Here we have the low pass filter effective impedance as Z2, just representation. Okay, actually we will know, we have to find what is the output voltages. V output, as we can see, V output is nothing but the resistance and that voltage drop, I mean the effective resistance Z2 divided by Z1 plus Z2. This is just the voltage division formula. You can clearly see that the output voltage V output dash is equal to Z1 divided by Z1, the total resistance Z1 plus Z2 into V input. Okay, the prime is, see, I have introduced prime there because we want to know what is the difference between the actual overall network. We have V in and V output, but right now I'm just considering the feedback network alone. That's why I'm having the notation V input prime and V output prime. Okay, V input prime, V output prime actually means that it is the input and the output of the feedback network. Okay, so consider Z2. If you see, R2 is parallel to the capacitor C2. So we have the effective impedances R2 parallel with 1/j into j omega C2. What is 1/j into c omega C2 is? It is the reactance. Okay, or we call that as a, what do you call that? I think it is reactance only. Okay, Xc is equal to, we have that value Xc is equal to 1 by omega C. I hope you remember that Xc is equal to omega C. That is the reactance. Okay, so Z2 is equal to R2 parallel with 1/j omega C2. Just remove this. Okay, and we have Z1. Z1 means, Z1, if you see, R1 is in series with C1. So I'm just directly adding the resistance R1 and the reactance 1/j omega C1 here. Okay, so this gives the impedance Z1. Now we are going to find what is the expression for V output and V input. So with this V output and V input, what is beta? Beta is nothing but V output dash divided by V input prime. V output prime divided by V input prime. So with that, we can easily find what is the value of beta there. Correct? Okay. Now, simplifying this Z2, we are converting to a mathematical form, because here we have a symbol parallel. So we are removing that. So we are representing, see, this is a simple calculation only. You can just do it by yourself. It is not a big deal. Okay. And now we are substituting in V output dash by V input dash, so that we will be having in the numerator, we will be having the Z2 divided by Z1 plus Z2 here. This is Z1 plus Z2. This complete thing is Z1 plus Z2. And we have, I think I have taken this V input dash to the denominator in the left side. So we have V output dash divided by V input dash with the now, if I am computing the phase of this V output by input, that means the angle of this V output dash by V output prime by V input prime, we have to compute that V output dash, the angle of this V output dash by V input dash means tan inverse of B by A. Do you remember, if I am having some network, you can see that if I am having some complex number A plus J beta, A plus JB, then the particular angle of this A plus JB is given by tan inverse of B by A. Okay, so tan inverse of B by A. Okay, yes, please mute yourself. Yeah, we have, if I am having a complex number A plus J beta, then the angle is tan inverse of B by A. That means the imaginary part divided by the real part. Okay, so here I don't have a real part here. Okay, so what happens is tan inverse of B means any omega R2 C1 divided by 0. That means tan inverse of infinity. That means we will be having 90 degree there. Okay, below also, if you are having if we have only this imaginary part alone, then 90 degree minus 90 degree will be equal to 0. That means the angle in the numerator minus the angle in the denominator. Okay, so if both the numerator and the denominator has the imaginary value only the imaginary value, then the effective angle will be 0, because 90 degree minus 90 degree. But here, if you notice here, I will change the, yeah, if you notice here we have a real part as well. Okay, this makes the angle not equal to 0, but actually we need an angle that should be equal to 0. Okay, only the term I have rounded here, if this value is equal to 0, only if this value is equal to 0, we can achieve the resonance. Okay, then only we can achieve the resonance. That means then only we can maintain the angle phi at, then only we can maintain the angle of this phase shift oscillate, the angle of this feedback network at 0. Okay, so we are making that as 0. We are taking that to our advantage. Okay, this term is made to 0, and if we rearrange that term, then omega will be equal to 1 by root of R1 R2 C1 C2, where omega, we know that omega is equal to 2 pi FR. Okay, so I can write FR is equal to 1 by 2 pi root of R1 R2 C1 C2. That is the resonant frequency of your Wien bridge oscillator. Okay, now, okay, we have made this guy, whatever I have circled, encircled here, we have made this guy to disappear now. We are making this guy to 0. Now we are end up with the equation. Okay, I'll rewrite it. We have made this guy to 0. Okay, right now we don't have this guy that I have encircled in the green color. We have only the remaining components. So this one and this will be getting cancelled, and we have V output dash by V input dash will be equal to the remaining term R2 C1 divided by C1 R1 plus C2 R2 plus C1 R2. Okay, now if R1 is equal to R2 and C1 is equal to C2, then we have what we have is this beta V output dash divided by V input dash is equal to 1 by 3. If I am substituting R1 and in place of R2, I am substituting R. In the place of C1 and C2, I am substituting C. Okay, then I will be having RC divided by 3RC. 3 RC. So RC getting cancelled, and we will be having only 1 by 3 there. Okay, that's why the beta, the value of the beta in the Wien bridge oscillator is equal to 1 by 3. Okay, basically your beta will be a fraction, because you are only going to take a fraction of your output and you are going to feed in the input. Okay, so this is about your Wien bridge oscillator. Fine. Okay, now I'm moving on. So this is an example problem of your Wien bridge oscillator. So we are trying to find the value of the resistor R. So see, I want to construct I want to design an oscillator which gives me a frequency of 10 kilohertz. Okay, that means I want a sine wave that is being generated at 10 kilohertz, and I have only a capacitor of 0.01 microfarad with me. Okay, I have capacitors of value only 0.0 megahertz, microfarad. Now I want to generate a frequency of 10 kilohertz. So what value of R I have to choose? That is the actual question here. Okay, so I am taking the formula directly. FR is equal to, because here we consider R1 is equal to R2 and C1 is equal to C2. So I am taking this expression straight away here, and we are substituting in the place of C. We are rewriting this equation because we need only R. So we are rewriting this equation like this, and we are substituting in the place of C, we are substituting 0.01 microfarad, and in the place of FR we are substituting 10 kilohertz. Okay, and correspondingly we will be getting a resistor value of 1.59 kilohertz. Only if you use such a combination, that means R is equal to 1.59 kilo ohms and capacitor is equal to 0.01 microfarad, then only you could able to generate a signal of frequency 10 kilohertz. Okay, this is about your Wien bridge oscillator. Okay, I hope you don't have any doubts till now. I will start the RC phase shift oscillator, and we will discuss a little bit detail in the next class. Okay, so I will start on this. Okay, so this is your RC phase shift oscillator. Okay, so there is another oscillator in the when we have the resistor and the capacitor components in your feedback network. That is the RC phase shift oscillator and the Wien bridge oscillator. Right now we have discussed about the just now we have discussed about the Wien bridge oscillator. Now we will be discussing about the RC phase shift oscillator. Okay, with this next 2 slides I will just end the class. Okay, actually your RC phase shift oscillator will have a, in the feedback side you can see you have only the RC combinations like this. I'll just circle it. Okay, here you have only that RC combinations. There is a reason why we are having 3 such combinations. Here we can see 3 stages of RC combinations. Okay, 3 stages of, I am trying to write it but it is very hard. 3 stages of RC combinations. 3 stages of RC combinations. Okay, the problem with the RC phase shift is it introduces a phase shift of 180 degree. Okay, so what happens is that accordingly you want to introduce another 180 degree phase shift in your actual amplifier A, then only you could get a oscillation without any feedback. I mean without any phase shift there. Okay, because previously in the Wien bridge oscillator your amplifier is connected to the non-inverting terminal. That means there won't be any phase shift there, and your Wien bridge feedback network will also does not introduce any feedback there. Any phase shift there in the feedback network also does not introduce any phase shift there. But here in the RC phase shift oscillator, this feedback network will introduce a phase shift of 180 degree, and because of this, we want to compensate this 180 degree to 0 degree. Okay. Now what we are doing is we are taking another 180 degree. This amplifier will introduce another 180 degree, so that effectively we will be having 360 degree phase shift. 360-degree phase shift means 360-degree phase shift means it is a 0-degree phase shift. Okay, so this is about the RC phase shift oscillator, and we will discuss about this in detail. Okay, right now I will show some circuit. This is a idealized phase shift oscillator because we have no information, we haven't included any information about this amplifier A. Okay, now we are considering two networks. One is a transistor, a transistor amplifier. Here you can see. Okay, this oscillator is designed using a transistor amplifier, and this is also an RC phase shift oscillator, and this oscillator is designed using an op amp. Okay, you can see. First, I will tell what this op amp guy will do. Here you can see the input is given to the negative input of the op amp, so it will introduce a phase shift of 180 degree. Okay, and also your RC combination will introduce a phase shift of 180 degree. So effectively in the output here we'll be getting a 360 degree phase shift. That means 360 degree is equivalent to 0 degree. Okay, this is about the op amp circuit. And when you see this particular circuit, you must be remembering the RC coupled amplifier. The only thing is you don't have the coupling. Okay, that is the difference. Okay, because we are not taking any input from some other device. We are taking it from some passive components only. Okay, that's why we are not including the coupling capacitors now. Fine. Okay, now here I am giving the feedback, taking the output, and I am getting I am giving the output as a feedback to the input of the amplifier. Here you can clearly see. I'll redraw this. Here you can see the output is given to the RC feedback network, and the part of the feedback network and on the output of the feedback network is given to the input here. Okay, this circuit is nothing but a RC coupled amplifier. Okay, and now if we check the frequency of the operation, it will be given by 1/2 pi RC. Okay, into, you have to notice here, this is into 1/√6 plus 4 into RC by R. Okay, anyway we will be seeing the derivation of the generalized, at least we will be seeing the frequency derivation of the generalized RC phase shift oscillator. Okay, in the next class. Okay, what happens because of this RC circuit? What is the effect of this RC circuit on the oscillator? That's what we will be going to discuss in the next class. Okay, I'll send you the material. You go through that, you keep on going through that, and at some day we will be discussing whatever doubts you have. Okay, I'll be available online for 1 hour on that day. Okay, thank you for now. You can give your attendance now. I will take a note of it. I'll cut this call. You give your attendance now.